Welcome back to the CSG Engineering Society YouTube CAD video series. This is part 2 of trying to learn how to read an engineering drawing. Okay, let's go over a couple holes, okay? The first one is a blind hole. This hole is also could be known as the simple hole as well, okay? So it's a simple drilled hole like so over here, okay? It just goes through. Nothing special about it. It will have a diameter symbol to showcase what's the diameter, and it will also have a depth symbol over here to showcase how far into the material it goes in. Once again, you'll notice that because this circle is not visible, because this hole is not visible from this view over here, it appears as a hidden line. But because the hole is created on this face over here, the hole has a visible line attached to it instead. And you'll notice the center lines as well, center line, and the center mark here, okay? Now, as for the counterbore hole, the counterbore hole starts with a bore first, an initial bore, and then the hole begins after. Let me show you a better view instead. So here's the bore, starts with a bore, and then the hole follows afterwards. Okay? For counterbore holes, you'll need to specify a couple of things, and I'll also show you where you'll go to specify this as well, okay? You need to specify the dimension of the hole itself, and then the diameter of the bore, okay? So the smaller hole over here is the actual hole, and then the larger hole over here, this is the boring diameter, okay? You'll also have the dimensions of the bore given to you as well. So this bore has gone in 10.8 millimeters deep, and then the hole itself has gone in 50 millimeters in deep, okay? This angle over here is just a result of the hole features that I used, but the hole features that I used, okay? And this was the default hole settings. Let me show you now. Let's go back to the modeling and the hole itself, okay? So obviously, you'll open up hole first, click on the surface, then you'll go over here to counterboard, and then click onto screw clearance. Now, when you're over here, you're going to make sure that you're in ISO. Click on this one over here. And then over here, then you can select the screw diameter as well. So using the metric 10, okay, M10. And keeping the fit as normal. And for some reason over here, which is a good thing as well, the bore diameter is fixed for you as well. Okay? Over here, you can specify the hole depth as well. Okay, so just as an update, it turns out that we don't need the bore depth because it will be given in the tool settings itself. Okay, so all you need to focus on is just on the counterbore, the hole size, and the depth of it as well. And you won't need to focus on the bore diameter either. Just go onto the hole settings, click on M10, and then specify the depth of it as well. Now for the countersunk hole, okay, or countersink hole, whichever one you want to call it. The countersink hole is similar to the counterbore, where it has a little region over here first, and then the hole follows after. Except for the countersink, it's shaped like a sink basically. So if I were to like view it like this instead, you can see how like it kind of like tapers in. Okay, so it's like a sink as well. So when you see this pattern, you immediately go to the hole tool, the hole feature over here, and you immediately then go to countersunk, and then you specify screw clearance, and then ISO flathead M10 normal, so this might be different, the screw size might be different, but the fit will always be normal, okay? We're just going to stick onto the normal fit. And then you'll specify the hole depth, okay? But in our case though, because of this part, it goes from one end and it exits out the other. So this is technically a through hole. So how you could specify this is you could do until next, and this would be a through hole, okay? So let me show you a through hole. If I would select that, it would end on that face over there. You see? It exits out of there. That's what a through hole is. See a through hole. And you can't see this hole because it's a hidden line. Okay? From this face you can't see the hole. And what you'll notice is that the countersunk hole is very similar to the counter bore hole. So always cross-reference with another view to see what kind of hole it is. Whether it's a counter bore hole or a countersunk hole. Or something else entirely. It could be something else entirely as well. So always just double check with another view before committing to a feature. When working with metric clearance countersunk holes, you will only need to focus on this M10 or the value that follows after the M and how deep it goes, whether it's a through hole or a hole and a hole that has like a specific dimension. So we'll specify, for example, okay, the dimension of the hole will be 100 and something millimeters deep in, okay? It will be specified. But that's the only thing. That's the only two things you have to focus on: just the depth of it and the metric size of it. Okay. Here is a threaded hole. So a threaded hole looks like this. Okay. This is a simplified drawing of it. This 3/4 view over here shows you what a threaded hole looks like from the top view. So looking at it straight on. Okay. If you see this 3/4 circle, it means that this is a threaded hole, okay? If you see it from the side though, how you can tell that it's a threaded hole is like a double layered wall over here, okay? So a double layered wall that kind of ends at some point, okay? Like so. So when you see this hole, you will immediately go to the application. So make sure that you're modeling. You'll go into hole and you will specify that the hole is threaded, making sure that you're on metric course, and then the size you can pick over here, the size of your metric hole as well. Keep this on 7.5. And then keeping the thread depth type as custom, and then over here then you have the options to specify the thread depth and the hole depth. Let's see what the difference is. So the thread depth is where the double line over here stops. That's the thread depth, so 50. And the hole depth is where it's not this point over here, it's this point over here, okay? It's where the hole finally ends, so 60 over here. For your threaded holes, you'll know that's a threaded hole if it not only has the metric written with it, so M something, not only that, but you have this X 1.5 or X something point something, okay? When you see this, this is the pitch. So the distance in millimeters between each spiral thread, okay? But you don't have to focus on too much on that. The 6H, however, this is the tolerance, and so you don't have to worry too much about it. You just have to maybe just keep this on radio engage as 7.5 and it will stay consistent, okay? I'm not 100% sure on this, but for our competition, I'll keep that value at 7.5. You might also see that it specifies over here right-handed or left-handed. And this just means, so right-handed just means that it screws in, so something screws in using a clockwise turning, and left-handed means that it screws in using an anti-clockwise turn, okay? But generally, for most, like 90% of screws made, I believe, off the top of my head, really, most screws will be right-handed. You can certainly buy stuff that are left-handed as well, but most of the stuff will be right-handed. Finally, we're now at the fillet and the chamfer. Okay. Now, for the fillet and the chamfer, how you can tell that they're as such is if you look at one of the other views. Okay. So for example over here, right, you can tell that it's a circular shape, and this shape over here has this kind of like diagonal shape to it over here. Okay. This will be a chamfer. Very likely this is a chamfer as well. Okay. Over here, how it kind of like merges together over here. This is a fillet. Okay. A chamfer and a fillet, like so. Okay. Chamfers, fillets. So chamfer, 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 and then the fillet over here, which is more like a blend. Okay. So if you see this, immediately think okay, I'm gonna have to at some point apply a fillet at the end. Okay. And over here, I've also just shown you a hole that was created not using the hole tool, but using the extruded cut feature. And what you'll notice is that it doesn't apply the angle over here, okay? As most other holes would, okay? So if you see this kind of flattened, then this is a flat end hole, okay? So there are some drill bits that do manufacture this way as well, but they're less common. But I just want to point this out because some people, they make holes using the extruded cut feature, and if they use it, this is the pattern that they'll get. And so you'll get a different volume compared to someone who actually did the proper hole, like so. Okay, so this is just a little warning to those who might be using the hole feature way too often. Sorry, the extruded cut feature way too often for making holes. Finally, let's apply all of this to analyze. This is basically a view from before, okay? So what you'll notice is that in the model, we have this extra line over here, but in the engineering drawing, we don't have it, okay? So starting from the center out, we have the first circle, then the second circle, this edge over here, this corner over here, and then we have the third edge over here, okay? This line over here is not modeled in the engineering drawing because it's just a tangent line. It's not an actual edge. You see, there's no real difference. There's no real distance, so we don't model it in engineering drawing. Okay. So if you see it, don't worry about it. You see over here the 4 holes. We have our center marks. You have the center marks over here. And we also have the center mark in the middle as well. We also have, in this angle, you'll see that there's a section view. You'll see that there's also a center line as well going through here, showing to us that this is a circular feature as well. We can also tell that this is the radius as well. This is a radii over here. And that all of the linear dimensions are also given as well. So from here to here, the diameters and such, okay? Okay, this should be enough material for you guys to be able to at least be able to read some of the engineering drawings for the competition coming up, okay? All right, thank you. Let's do a quick recap before we wrap up. First, we went over how to read an engineering drawing, starting from views, then moving through dimensions, edges, and finally holes and features. Second, remember that while we mentioned tolerances, for this CAD competition, we're only working with nominal dimensions. Even when you're creating holes, if you see tolerance callouts like 6H, don't worry. The metric hole series in NX will automatically size everything for you, except for the hole depth and the thread type. So M8, for example, or M10. If NX asks for radial clearance, just use 0.75 millimeters. That keeps everyone consistent across models. I'll also link a great YouTube video that explains how important it is for designers like you in the future to communicate clearly with technicians and machinists. That collaboration is what turns designs into real working parts, not just here at university, but also throughout your engineering career. Thank you.